Welcome everyone. So today I brought with me a spring, which is an object that you can change its shape and length by pulling on it, and which when you stop pulling on it will return to its original configuration. We'll be using that to try to come up with a strong model for describing spring forces, which are the forces that springs will exert on something if you attach the spring to the end of it. So that's our objective today. We're going to use a model for springs, which is known as Hooke's law, which again assumes that my spring does not deform during the course of stretching it out. If you've ever had an old school slinky and pulled on it too hard, you know that you can bend the metal out of shape. Then it's not going to act like a good spring anymore. But as long as you don't pull too hard on it, your spring is likely to be well described by Hooke's law, which says that the spring force, which I'll label with an S, is equal to the spring constant, which we'll symbolize with the letter K, times the position that the spring has been displaced from its equilibrium position. And in particular, springs will oppose this change in position, so we want to put a negative sign here. So to help me instantiate this, I'll think again about my little spring here. So if, for example, I pull on this spring, what I'm doing is displacing it from equilibrium, which will make x bigger and bigger while the equilibrium position stays the same. Making the entire displacement in here bigger, which will make the spring force bigger, but in the opposite direction. So as I pull the two ends of the spring apart, it will pull back on my hands to try to get the spring back into its initial configuration. What's interesting about springs is that this expression works in both directions. So if I compress the spring instead of extending it, it will push back outwards again to try to get to its initial configuration. As I said, this constant K is known as the spring constant, and it will end up telling us a little bit about how strong or how stiff the spring is. And this expression here is typically called the displacement, or the displacement from equilibrium. And often it is convenient to choose a coordinate system so that the equilibrium position is 0. And then I could simplify this expression and simply write it as minus kx. That can be a much easier expression to deal with, again, with the assumption that the equilibrium position is set to 0.